Hello there, and welcome to the Sleepy Science Channel. Tonight, we will be journeying through the deepest mysteries of existence itself, exploring cosmology, the study of our universe as a whole, from its fiery beginning to its distant fate, from the smallest quantum fluctuations to the largest structures spanning billions of light years. We will drift through the story of everything that is, was, and ever will be. If you enjoy these quiet explorations, I invite you to like and subscribe, or share a simple thought down in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the calm of cosmic time to carry you gently into sleep. Let's begin. The birth of everything. The universe began in an instant of unimaginable transformation. Around 13.8 billion years ago, everything we know, all matter, all energy, all space itself, emerged from a singular point of infinite density and temperature. This moment is known as the Big Bang. Though it was not an explosion in the traditional sense, there was no space for anything to explode into. Instead, space itself began expanding, carrying energy outward in all directions at once. In that first instant, the universe was smaller than an atom, yet it contained all the potential for everything that would ever exist. The temperature was so high that no particles as we know them could form. Only pure energy filled this newborn cosmos. Energy so concentrated that it shaped the very fabric of reality. Within the first fraction of a second, the universe expanded faster than the speed of light, a period known as cosmic inflation. This rapid expansion smoothed out irregularities and set the stage for the universe we observe today. It stretched tiny quantum fluctuations into patterns that would eventually become galaxies, stars, and planets. The Big Bang was not just the beginning of matter and energy, it was the beginning of time itself. Before that moment, the concept of before had no meaning. There was no time, no space, no anything waiting to begin. The universe emerged from nothing, or perhaps from something we cannot yet comprehend. To think that every atom in your body, every star in the sky, every galaxy we observe, all originated from that single point, is both humbling and awe-inspiring. The Big Bang set in motion the entire cosmic story, a narrative still unfolding around us today, the cosmic microwave background. The universe was once so hot that light could not travel freely. In the earliest moments after the Big Bang, the cosmos was filled with a dense plasma of particles and radiation. This plasma was so thick, so opaque, that light could not move through it. Photons, the particles of light, would travel only a tiny distance before colliding with an electron or proton and bouncing back. The universe was essentially a glowing fog. For nearly 400,000 years, this state persisted. The universe was expanding and cooling, but it remained opaque. Then, as temperatures dropped to around 3,000 degrees, something remarkable happened. Electrons and protons combined to form neutral hydrogen atoms. This moment is called recombination, and it fundamentally changed the nature of the cosmos. With neutral atoms forming, photons were suddenly free to travel without constant collisions. Light could finally stream through space unimpeded. This moment, when the universe became transparent, released a flood of radiation that has been traveling through space ever since. We call this the cosmic microwave background radiation, and it fills the entire universe. Today, after billions of years of expansion, this radiation has cooled to just 2.7 degrees above absolute zero. It appears not as visible light, but as microwaves. Special telescopes can detect this faint glow coming from every direction in the sky. It is the oldest light in the universe, a snapshot of what the cosmos looked like when it was just a tiny fraction of its current age. The cosmic microwave background is remarkably uniform, showing that the early universe was incredibly smooth. But tiny variations exist, temperature differences of just a few millionths of a degree. These tiny ripples represent the seeds of all structure we see today. Regions that were slightly denser attracted more matter and eventually collapsed to form galaxies, while less dense regions became the vast voids between them. When you tune an old television to a channel with no signal, a small fraction of the static you see comes from this ancient radiation. You are literally watching the afterglow of creation. Photons that have traveled for over 13 billion years to reach your screen. The cosmic microwave background connects us directly to the birth of the universe, a whisper from the dawn of time. The first atoms form. In the extreme heat of the early universe, even atoms could not exist. For the first few minutes after the Big Bang, the cosmos was too hot for atomic nuclei to remain stable. Protons and neutrons existed, but they bounced around violently in the intense heat. Any nuclei that formed were immediately torn apart by high-energy photons. This era of the universe was a chaotic dance of fundamental particles. As the universe expanded, it cooled. Within the first 3 minutes, temperatures dropped enough for the first atomic nuclei to form in a process called Big Bang nucleosynthesis. Protons and neutrons began fusing together, creating the lightest elements. The vast majority formed simple hydrogen nuclei, which are just single protons. About 25% of the mass became helium nuclei, containing 2 protons and 2 neutrons. Tiny amounts of other light elements also formed, including deuterium, a heavy form of hydrogen, and trace amounts of lithium and beryllium. But the expansion and cooling happened too quickly for heavier elements to form. After just a few minutes, the temperature had dropped below the threshold needed for nuclear fusion. The production of elements stopped, and the universe was left with mostly hydrogen and helium. These first elements would drift through space for hundreds of thousands of years before electrons joined them to create complete atoms. The ratio of hydrogen to helium created in those first minutes matches what we observe in the universe today. This agreement is one of the strongest pieces of evidence supporting the Big Bang theory. The elements forged in that brief window provided the raw material for everything that came after. Without those first atoms, there would be no stars, no planets, and no life. Every hydrogen atom that ever existed, including those in water molecules and in your own body, formed in the first moments of the universe. The helium that fills balloons and makes voices sound funny was created in the cosmic furnace billions of years before Earth even existed. We are connected to that ancient moment in the most literal way possible, the dark ages of the universe. After recombination freed light to travel through space, the universe entered a long period of darkness. This era, lasting hundreds of millions of years, is known as the Cosmic Dark Ages. It is called dark, not because there was no light, but because there were no sources of visible light as we know them today. The stars had not yet been born. During this time, the universe was filled with neutral hydrogen gas, slowly drifting through space. The only light came from the fading cosmic microwave background, gradually redshifting into invisibility as the universe expanded. Gravity was at work, pulling together the slightly denser regions, seeded by those tiny fluctuations in the cosmic microwave background. Slowly, imperceptibly, clouds of hydrogen gas began to collapse under their own gravity. These clouds grew denser and denser, their centers heating up from the compression. For millions of years, this process continued in darkness. The universe was patient, allowing gravity to do its slow work of gathering matter together. No eyes existed to watch this transformation, no observers to mark the passage of time. Eventually, deep within the densest clouds, pressures and temperatures reached a critical threshold. Hydrogen atoms were crushed so tightly that their nuclei began to fuse, releasing enormous amounts of energy. At that moment, the first stars ignited. Light returned to the universe after hundreds of millions of years of darkness. These first stars were unlike any that exist today. They were massive, perhaps hundreds of times more massive than our sun, burning with incredible intensity. They lived fast and died young, exploding as supernovae after just a few million years. But their brief lives were transformative. They produced the first heavy elements, carbon, oxygen, iron, and others. Scattering them into space when they died, they began the process of enriching the universe with the building blocks of planets and life. The Dark Ages ended as the first galaxies formed from clusters of these early stars. Light once again filled the cosmos, but it was a different light than before. It came from stars, from fusion, from the conversion of matter into energy. The universe had entered a new chapter, one that continues to this day: the formation of galaxies. Galaxies are not random collections of stars scattered through space. They are the result of billions of years of gravity organizing matter into vast structures. The first galaxies were small, irregular collections of stars formed from the densest regions of gas in the early universe. They were unlike the grand spirals and ellipticals we see today, more like the building blocks that would eventually merge to form larger structures. As time passed, these proto-galaxies began to interact. Gravity drew them together, and they merged to form larger galaxies. This process of hierarchical structure formation continues even today. Small galaxies merge to form medium ones, which merge to form large ones. Our own Milky Way galaxy is the product of countless mergers over billions of years. Within these early galaxies, stars formed in great bursts, creating stellar populations that enriched the gas with heavy elements. Each generation of stars added more complexity to the chemical composition of the universe. Black holes formed at the centers of these galaxies, growing as they consumed nearby matter. These black holes would eventually become the supermassive monsters we find at the hearts of most large galaxies today. Galaxies do not form in isolation. They cluster together under gravity's influence, creating groups and larger clusters. These clusters themselves form even larger structures called superclusters. Between these structures lie vast cosmic voids, enormous regions of space with very few galaxies. This cosmic web of galaxies, clusters, and voids spans the entire observable universe. The filamentary structure of the cosmic web formed from those tiny density variations in the early universe. Computer simulations show how gravity amplified these small differences over billions of years, creating the large-scale structure we observe. The patterns we see in galaxy surveys match remarkably well with predictions from theory, confirming our understanding of cosmic evolution. To see galaxies is to see billions of years of cosmic history written in light. Each galaxy is a city of stars, a gravitationally bound system containing hundreds of billions of suns. They are the fundamental building blocks of the visible universe, islands of light, separated by vast expanses of darkness. And yet, for all their grandeur, galaxies represent only a small fraction of what the universe contains. Dark matter holds galaxies together. When astronomers measured the rotation of galaxies, they discovered something surprising. Stars at the edges of galaxies were moving much faster than they should be, based on the visible matter present. According to the laws of gravity, stars farther from the galactic center should move more slowly. just as outer planets in our solar system orbit more slowly than inner ones. But this is not what observations showed. Instead, stars across galaxies rotate at roughly the same speed, creating flat rotation curves that defied explanation based on visible matter alone. Either our understanding of gravity was incomplete, or there was additional matter present that we could not see. Multiple lines of evidence pointed to the second explanation. The universe contains far more matter than meets the eye. This invisible substance is called dark matter, and it makes up about 85% of all matter in the universe. It does not emit, absorb, or reflect light, making it completely invisible to telescopes. We detect its presence only through its gravitational effects. Dark matter forms vast halos around galaxies, providing the additional gravity needed to explain their rotation curves. Computer simulations of galaxy formation fail without dark matter. Only when dark matter is included do simulations produce galaxies that match what we observe. Dark matter appears to have been crucial in forming structures in the early universe. Its gravity helped pull ordinary matter together to form the first stars and galaxies. Without dark matter, the universe would look completely different if galaxies could form at all. We do not know what dark matter is made of. It is not ordinary atoms or molecules. It must be some exotic particle that interacts very weakly with normal matter. Physicists have proposed many candidates, from WIMPs, weakly interacting massive particles, to axions, to primordial black holes. Despite decades of searching, dark matter particles have not been directly detected. This mystery is humbling. The universe contains vast amounts of matter in a form we cannot see, made of particles we cannot identify. The stars, planets, and all the matter we can observe represent only a small fraction of what exists. We live in a universe that is mostly invisible, its nature hidden from our current understanding. Dark matter reminds us how much we have yet to learn about the cosmos. Dark energy accelerates expansion. The expansion of the universe is not slowing down as scientists once expected. In the late 1990s, two teams of astronomers were measuring distant supernovae to determine how the expansion rate of the universe was changing over time. They expected to find that gravity was gradually slowing the expansion, an effect left over from the initial push of the Big Bang. Instead, they discovered something completely unexpected. The expansion of the universe is accelerating. Distant galaxies are moving away from us faster and faster as time goes on. This discovery was so surprising that it took years for the scientific community to accept it. It earned the researchers the Nobel Prize in Physics in 2011. The cause of this acceleration is called dark energy, though the name simply reflects our ignorance about its nature. Dark energy appears to be a property of space itself, an intrinsic energy density that exists everywhere. As space expands, more dark energy comes into existence because there is more space. This creates a repulsive effect that drives acceleration. Dark energy dominates the energy content of the universe, making up about 68% of everything. Combined with dark matter at 27%, ordinary matter, the stuff of stars, planets, and people, accounts for less than 5% of the universe. We are cosmically insignificant in terms of mass and energy, living in a universe dominated by things we do not understand. Several theories attempt to explain dark energy. It might be Einstein's cosmological constant, a property he added to his equations and later called his greatest blunder. It might be a new field pervading space, dubbed quintessence by some researchers. Or it might indicate that our understanding of gravity needs modification on the largest scales. Each possibility has profound implications for the ultimate fate of the universe. The discovery of dark energy transformed cosmology. It revealed that we live in a universe very different from what we imagined. The gentle deceleration we expected has been replaced by an ever-increasing expansion. As billions of years pass, distant galaxies will accelerate away from us, eventually moving faster than light can travel through the expanding space between us. In the far future, they will disappear beyond our cosmic horizon forever. The observable universe has boundaries. The universe may be infinite, but we can only see so far. Light travels at a finite speed, and the universe has a finite age. This means there is a maximum distance from which light has had time to reach us since the Big Bang. This defines the observable universe, a sphere centered on Earth with a radius of about 46 billion light-years. You might wonder why this radius is larger than the age of the universe, times the speed of light. The reason is that space itself has been expanding while that light traveled toward us. Galaxies that emitted light 13 billion years ago are now much farther away than 13 billion light-years, because the space between us has stretched during the light's journey. The observable universe contains everything we can potentially see or interact with. Beyond its edge lies more universe, possibly infinitely more, but we cannot observe it. Light from those distant regions has not had time to reach us yet. As time passes, the observable universe grows larger as light from more distant regions arrives, though the accelerating expansion complicates this picture. The edge of the observable universe is not a physical barrier. It is simply a horizon beyond which we cannot see. Different observers in different parts of the universe have their own observable universes, overlapping with ours, but not identical. An observer in a galaxy at the edge of our observable universe would see a completely different set of distant galaxies on their far horizon. This cosmic horizon means we can never know if the universe is truly infinite or merely very large. We can study only the observable portion. The universe beyond our view remains forever mysterious, its nature unknowable unless the fundamental laws of physics allow some form of faster-than-light communication or travel, which they appear not to do. Within the observable universe, we can count roughly 2 trillion galaxies, each containing hundreds of billions of stars. The total number of stars exceeds the number of grains of sand on all the beaches of Earth. And yet, this vast cosmic census represents only what we can see. The true universe may be far larger, perhaps infinite, extending forever beyond our cosmic horizon. The universe is mostly empty space. Despite containing trillions of galaxies, the universe is overwhelmingly empty. The distance between stars is vast compared to their sizes. If you scaled the sun down to the size of a grapefruit, the nearest star would be thousands of miles away. The space between galaxies is even more dramatic. The Milky Way and Andromeda, our nearest large galactic neighbor, are separated by about 2.5 million light-years of nearly empty space. This emptiness is not a void in the traditional sense. Space itself has properties. It can expand, carry energy in the form of dark energy, and support the propagation of fields and waves. But in terms of matter, the universe is extremely sparse. The average density of matter in the universe is less than 1 hydrogen atom per cubic meter, far emptier than the best vacuum we can create on Earth. Even within galaxies, stars are separated by vast distances. Our solar system is a tiny oasis in an ocean of space. The nearest stars are light-years away. Between them lies darkness, interrupted only by tenuous clouds of gas and dust. The emptiness between galaxies is even more profound, broken only by occasional tendrils of hot gas stretched along the cosmic web. This emptiness is crucial to the universe's structure. If space were densely packed with matter, gravity would have caused everything to collapse long ago. The vast distances between objects allow the universe to expand and evolve over billions of years. The emptiness provides the stage on which cosmic evolution plays out. The emptiness also means that interstellar travel, if it ever becomes possible, would require journeys of unimaginable duration. Even traveling at the speed of light, it would take years to reach the nearest stars, and millions of years to cross between galaxies. The cosmic voids ensure that most of the universe remains forever out of reach, separated from us by distances too great to cross in any reasonable time. Yet this emptiness is not sterile or meaningless. It is the canvas on which existence is painted. The space between stars allowed planets to form, including Earth. The space between galaxies provided room for them to grow and evolve without constant destructive collisions. The emptiness of the universe is as essential to its nature as the matter and energy it contains. Cosmic inflation explains uniformity. The cosmic microwave background reveals that the early universe was remarkably uniform in all directions. Regions, separated by vast distances, far too great for any signal to have traveled between them at the speed of light, nevertheless have nearly identical temperatures. This presents a puzzle known as the horizon problem. How did these causally disconnected regions come to have the same properties? The solution is cosmic inflation, a brief period of exponentially rapid expansion that occurred in the first fraction of a second after the Big Bang. During inflation, the universe expanded by a factor of at least 10 to the 26th, growing from subatomic scales to perhaps the size of a grapefruit or larger. This expansion happened faster than the speed of light, which is allowed because space itself was expanding. Before inflation, the entire observable universe was small enough that all regions could have been in thermal equilibrium. They had time to reach the same temperature. Then inflation stretched these causally connected regions apart so rapidly that they became separated by distances light could not cross. This explains why opposite sides of the sky have the same temperature, despite never being in contact after inflation ended. Inflation also explains why the universe is so flat. The geometry of space can be curved, like the surface of a sphere or a saddle, or it can be flat, like an infinite plane. Observations show that our universe is extremely close to flat. Inflation explains this by stretching any initial curvature until it becomes negligible. Just as the surface of a balloon appears flatter as you inflate it, the tiny quantum fluctuations that existed before inflation were also stretched to enormous scales. These stretched fluctuations became the seeds of all structure in the universe, the slight overdensities that eventually collapsed to form galaxies. Inflation took the randomness of quantum mechanics at the smallest scales and imprinted it across the cosmos, creating the patterns we observe in the distribution of galaxies today. Inflation remains a hypothesis, though it is widely accepted because it explains multiple features of the universe so elegantly. Direct evidence for inflation would come from detecting primordial gravitational waves imprinted on the cosmic microwave background. Experiments are currently searching for this signature, which would provide a window into physics at energy scales far beyond what particle accelerators can achieve. The universe has no center. When we observe distant galaxies moving away from us in all directions, it is tempting to think that we are at the center of the universe. But this is an illusion of perspective. Every observer, anywhere in the universe, would see the same pattern. From any vantage point, galaxies appear to be receding, with more distant ones moving faster. The expansion has no center. This seems paradoxical at first. How can everything be moving away from everything else? The answer lies in understanding that space itself is expanding. Galaxies are not moving through space away from a central point. Rather, Space between galaxies is growing, carrying them apart. Imagine dots on the surface of an inflating balloon. As the balloon expands, every dot moves away from every other dot, but none is at the center. The Big Bang did not happen at a point in space. It happened everywhere simultaneously. Every location in the universe was part of that initial state. There is no special location where the Big Bang occurred that we could point to and say, there is the center. Space itself emerged from the Big Bang and has been expanding ever since. This concept challenges our intuition because all explosions we experience have a center. But the Big Bang was not an explosion into existing space. It was the beginning of space itself. Asking what is at the center of the universe is like asking what is north of the North Pole. The question assumes a framework that does not apply. Some cosmologists speculate that the universe might be infinite. If so, it has always been infinite. Even at the moment of the Big Bang, an infinite universe has no center by definition. Every point is equivalent to every other. Even if the universe is finite but without edges, like the surface of a sphere, it still has no center. A being living on the surface could travel forever without finding an edge or a central point. The absence of a cosmic center is liberating in its way. It means Earth occupies no special position in the universe. We are not central, but we are not peripheral either. Every location is equal. The view from here is representative of the view from anywhere else. This principle, called the cosmological principle, underpins modern cosmology and has been confirmed by observations in all directions. Redshift reveals cosmic expansion. When light travels through expanding space, its wavelength stretches along with space itself. This stretching shifts light toward longer wavelengths, toward the red end of the spectrum, a phenomenon called cosmological redshift. The amount of redshift tells us how much the universe has expanded since the light was emitted. A galaxy with a high redshift is seen as it was when the universe was much smaller and younger. Astronomers measure redshift by examining the spectrum of light from distant objects. Chemical elements produce characteristic patterns of absorption or emission lines at specific wavelengths. By comparing these patterns to those measured in laboratories on Earth, astronomers can determine how much the wavelengths have been stretched. This directly reveals how much the universe has expanded since that light began its journey. The relationship between redshift and distance is not straightforward because the expansion rate has changed over cosmic history. Light from very distant galaxies has traveled for so long that the universe has undergone significant evolution during its journey. The expansion was slower in the past when matter and radiation dominated, and it has accelerated more recently as dark energy took over. The most distant objects we can observe have redshifts greater than 10, meaning their light has been stretched by more than a factor of 10. These objects are seen as they appeared when the universe was less than 1 billion years old, just emerging from the dark ages. Their light has traveled for over 13 billion years to reach us, though the objects themselves are now much farther away due to continued expansion. Redshift is one of the most powerful tools in cosmology. It allows us to look back in time, observing the universe at different stages of its evolution. By studying galaxies at various redshifts, astronomers can trace how galaxies have changed over billions of years, how the star formation rate has evolved, and how the large-scale structure of the universe has grown. Redshift turns telescopes into time machines. The discovery that redshift increases with distance, made by Edwin Hubble in the 1920s, was the first evidence that the universe is expanding. This observation transformed cosmology from a philosophical speculation into an observational science. It showed that the universe has a history, a beginning, and an evolution. The measurement of cosmic redshift continues to be central to cosmology today. The Hubble constant measures expansion rate. The rate at which the universe expands is quantified by the Hubble constant, named after Edwin Hubble, who first measured it. The Hubble constant relates the velocity at which galaxies recede from us to their distance. Its value tells us how fast the universe is expanding right now. Measuring this constant precisely is one of the most important goals of observational cosmology. The Hubble constant is expressed in units of kilometers per second per megaparsec. A megaparsec is about 3.3 million light-years. The current best estimates place the Hubble constant around 70 kilometers per second per megaparsec, meaning that a galaxy 1 megaparsec away recedes at 70 kilometers per second, while 2 megaparsecs away recedes at 140 kilometers per second, and so on. Measuring the Hubble constant requires determining both the distances and velocities of galaxies. Velocities are relatively easy to measure through Redshift. Distances are much harder, requiring a cosmic distance ladder built on multiple methods. Astronomers use Cepheid variable, stars, supernovae, and other standard candles to calibrate distances at increasing scales, each method building on the one before. Recently, a tension has emerged in cosmology. Different methods of measuring the Hubble constant give slightly different values. Measurements using the cosmic microwave background and the early universe give a value around 67, while measurements using local supernovae and stars give values around 73. This discrepancy is small, but statistically significant, and it persists despite careful checks. This Hubble tension, as it is called, could indicate new physics. Perhaps dark energy is not constant but evolves over time. Perhaps there is additional physics in the early universe not captured in our standard models. Or perhaps there are subtle systematic errors in one or more measurement methods. Resolving this tension is a major focus of current research. The Hubble constant also allows us to estimate the age of the universe. If we know how fast the universe is expanding now, we can run the clock backward to determine when everything was together. This gives an age of about 13.8 billion years, consistent with other methods of age determination. The Hubble constant connects the universe's expansion to its age and ultimate fate. The fate of the universe. The ultimate fate of the universe depends on its composition and the nature of dark energy. For decades, cosmologists debated whether the universe would expand forever or eventually collapse. If there was enough matter, gravity would eventually halt the expansion and cause everything to fall back together in a big crunch, a reverse of the Big Bang. If there was too little matter, expansion would continue forever. The discovery of dark energy changed this picture. With dark energy causing accelerated expansion, the universe appears destined to expand forever, and at an ever-increasing rate. Distant galaxies will accelerate away from us until they cross beyond our cosmic horizon. In the far future, observers in our galaxy will see only local galaxies, with the rest of the universe having receded beyond visibility. As expansion continues, galaxies will become increasingly isolated. The space between them will grow so vast that no light or signal can cross from one to another. Each galaxy cluster will become its own isolated island universe, cut off from all others. The rest of the cosmos will exist, but remain forever unreachable, separated by space, expanding faster than light can traverse. Stars will continue to form for many billions of years, but eventually the raw materials for star formation will be exhausted. Existing stars will burn out and die, and no new ones will replace them. The universe will grow darker as stars fade one by one. After trillions of years, all ordinary stars will have died, leaving behind only fading embers, white dwarfs, neutron stars, and black holes. The very distant future is harder to predict with certainty. If dark energy remains constant, the accelerating expansion will continue indefinitely. Some speculate it might even increase, leading to a big rip where space expands so rapidly that it tears apart galaxies, then stars, then planets, then atoms themselves. Alternatively, dark energy might decay or reverse, potentially leading to a future collapse after all. On the longest timescales, even black holes will evaporate through Hawking radiation, a quantum mechanical process that causes them to slowly lose mass. After perhaps 10 to the 100 years, even the largest black holes will have vanished, leaving behind only a cold, dilute soup of particles and radiation. The universe will reach a state of maximum entropy, with no structure, no order, no change. This is sometimes called the heat death of the universe. Yet even in this seemingly bleak future, there are unknowns. Our understanding of physics might be incomplete. New discoveries could reveal pathways to continued existence or even to new universes arising from quantum fluctuations. The ultimate fate remains uncertain, a reminder that despite our knowledge, profound mysteries about the cosmos remain. The multiverse hypothesis. Some theories in physics suggest that our universe might be one among many, perhaps infinitely many. This collection of universes is called the multiverse. Different versions of the multiverse hypothesis arise from different areas of physics, each with its own implications and controversies. One version emerges from cosmic inflation. If inflation occurred in our region of space, it likely occurred in other regions as well. Some models predict that inflation is eternal, continuously creating new expanding regions, each of which could become a separate universe with its own properties. These pocket universes would be forever separated from each other by inflating space between them. Another version comes from string theory, which predicts a vast landscape of possible vacuum states, perhaps 10 to the 500 different possibilities. Each vacuum state would have different physical laws, different particle masses, different force strengths. If all these possibilities are realized somewhere, then countless universes exist with varying properties, most very different from ours. Quantum mechanics suggests yet another form of multiverse. In the many worlds interpretation, every quantum measurement causes the universe to split into multiple branches, each representing a different outcome. This would create an enormous, perhaps infinite, collection of parallel universes, all equally real, each following a different history of quantum events. The Anthropic principle becomes relevant in multiverse scenarios. If countless universes exist with different properties, it is not surprising that we find ourselves in one where conditions allow life to exist. Universes with very different properties might not produce galaxies, stars, planets, or the chemistry needed for life. We exist in this universe because we could not exist in most others. Critics argue that the multiverse is not science because we cannot observe other universes. If something is fundamentally unobservable, can we ever confirm it exists? Supporters counter that many theories predict unobservable entities, and we accept them if they explain what we can observe. The multiverse might be a consequence of theories we can test in other ways. Whether the multiverse exists remains one of the deepest questions in cosmology. If true, it would mean that everything we observe, all the galaxies, all the matter and energy, all of cosmic history, is just one small part of a vastly larger reality. Our universe would be like a single bubble in an infinite cosmic foam, its properties just one possibility among countless others. Fine-tuning of physical constants. The laws of physics contain various constants, numbers like the strength of gravity, the charge of the electron, and the mass of the proton. These values seem arbitrary. They could, in principle, be different. But if they were even slightly different, the universe would be dramatically altered, likely in ways that would prevent life from existing. For example, if gravity were stronger, stars would burn out much faster, leaving no time for planets to form and life to evolve. If gravity were weaker, stars might not form at all, as clouds of gas would not collapse. The electromagnetic force must have its specific strength to allow atoms to exist with stable electron orbits. If it were different, chemistry as we know it would be impossible. The masses of fundamental particles also appear fine-tuned. If quarks were slightly heavier or lighter, protons and neutrons might be unstable, preventing the formation of atomic nuclei. The difference in mass between protons and neutrons is crucial. Change it by a small amount, and nuclear physics would not support the formation of the elements needed for life. Even the cosmological constant, related to dark energy, appears fine-tuned. Its value is incredibly small, but not zero. Theory suggests it could be enormous, which would have caused the universe to expand so rapidly that no structures could form. Why does it have the tiny but non-zero value we observe? This is called the cosmological constant problem and remains unsolved. Some see fine-tuning as evidence for design, suggesting that the universe was intentionally created to support life. Others point to the multiverse as an explanation. If countless universes exist with varying constants, we naturally find ourselves in one where the constants permit our existence. Both interpretations raise profound philosophical questions about the nature of reality. The fine-tuning of constants shows how delicate cosmic balance is. The universe operates on a knife edge, where small changes would lead to radically different outcomes. Whether this reflects design, selection from a multiverse, or some deeper principle we do not yet understand, it reveals that our existence depends on a remarkable concordance of values in nature's fundamental parameters. The cosmological constant problem. Einstein introduced the cosmological constant into his equations of general relativity as a way to create a static universe, counteracting gravity's pull. He later abandoned it after Hubble's discovery of cosmic expansion, but quantum field theory predicts that empty space should have energy, a vacuum energy that acts like Einstein's cosmological constant. The problem is that quantum field theory predicts a cosmological constant that is about 10 to the 120 times larger than what we observe. This is the worst prediction in the history of physics. If vacuum energy were really that large, the universe would have expanded so rapidly that atoms could never have formed, let alone galaxies or life. Yet observations show that the cosmological constant, dark energy, does exist, but with an incredibly small value. Why is it so small compared to quantum predictions, but not exactly zero? This is the cosmological constant problem. Attempts to explain it have led to proposals ranging from supersymmetry to extra dimensions, to modifications of quantum field theory itself. Some researchers invoke the Anthropic principle. Perhaps the cosmological constant varies across a multiverse, and we observe a small value simply because large values would not allow observers to exist. This explanation is controversial because it seems to give up on finding a deeper reason for the value we observe. The cosmological constant problem highlights a fundamental gap in our understanding. Something crucial is missing from our theories, either in how we calculate vacuum energy or in how gravity responds to it. Solving this problem might require a quantum theory of gravity, unifying quantum mechanics with general relativity, a goal that has eluded physicists for decades. Gravitational waves ripple through space-time. Einstein predicted that accelerating masses should produce ripples in space-time itself, traveling outward at the speed of light. These gravitational waves stretch and squeeze space as they pass, but the effect is incredibly tiny. For a century after Einstein's prediction, they remained undetected, too weak for any instrument to measure. That changed in 2015, when the LIGO detectors in the United States recorded gravitational waves from two merging black holes over 1 billion light-years away. The signal lasted just a fraction of a second, but it matched theoretical predictions perfectly. The collision of these massive objects released more power in gravitational waves than all the stars in the observable universe emit in light. Since that first detection, dozens more gravitational wave events have been observed, from merging black holes and neutron stars to other exotic collisions. Each detection opens a new window on the universe. Gravitational waves carry information different from light, revealing events that produce little or no electromagnetic radiation. The waves stretch and compress space by a tiny amount, less than the width of a proton over distances of several kilometers. LIGO detects this by using laser interferometry to measure the relative lengths of two perpendicular arms with extraordinary precision. When a gravitational wave passes, one arm stretches slightly while the other compresses, creating a measurable signal. Gravitational waves travel at the speed of light, but are produced by very different phenomena than electromagnetic waves. They can pass through matter unimpeded, carrying undistorted information from the hearts of colliding black holes, or from the moments after the Big Bang. They provide a complementary view of cosmic events, filling in details that light alone cannot reveal. Future gravitational wave observatories in space will detect lower frequency waves from even more massive sources, like supermassive black holes merging at the centers of colliding galaxies. These observations will trace the growth of structure in the universe and potentially detect gravitational waves from the inflationary epoch, providing a direct probe of physics at the highest energies ever accessible. Black holes curve space-time infinitely. Black holes are regions where gravity becomes so strong that space-time curves in on itself. At the center lies a singularity, a point where density becomes infinite and the known laws of physics break down. Surrounding the singularity is the event horizon, the boundary beyond which nothing, not even light, can escape. The event horizon is not a physical surface, but a point of no return. Once anything crosses it, all paths through space-time lead inexorably inward to the singularity. Time and space swap roles inside a black hole. Moving inward is as inevitable as moving forward in time is outside. Nothing can prevent reaching the singularity once the horizon is crossed. From outside, black holes appear frozen. Due to time dilation effects, an observer watching something fall into a black hole would see it slow down, redden, and fade, never quite crossing the horizon. But for the infalling object, the journey continues normally. They would cross the horizon and reach the singularity in a finite time by their own clock. Black holes are not empty voids. They have mass, spin, and potentially electric charge. They warp space-time around them, affecting the motion of nearby stars and gas. Matter falling into a black hole heats up due to friction and compression, often creating brilliant accretion disks that shine brightly before crossing the event horizon. Stephen Hawking showed that black holes are not completely black. Quantum effects near the event horizon cause them to emit radiation, now called Hawking radiation. This radiation carries away energy, causing black holes to slowly evaporate over immense timescales. A stellar mass black hole would take longer than the current age of the universe to evaporate. But given enough time, even black holes must die. The study of black holes tests the limits of physics. They are laboratories for extreme gravity, where general relativity and quantum mechanics must both be relevant. Understanding what happens at a black hole's singularity requires a theory of quantum gravity, which remains elusive. Black holes guard the deepest secrets of space-time itself. Time dilation makes time relative. Time is not absolute. It flows at different rates depending on motion and gravity. This effect, called time dilation, is a consequence of special and general relativity. An astronaut traveling near the speed of light would age more slowly than someone remaining on Earth. This is not an illusion but a real physical effect, confirmed by precise measurements. Gravity also dilates time. The stronger the gravitational field, the slower time passes. A clock on the ground floor of a building ticks slightly slower than one on the top floor. The difference is tiny but measurable with atomic clocks. GPS satellites must correct for time dilation effects because they orbit high above Earth, where gravity is weaker and time runs slightly faster. Near a black hole, time dilation becomes extreme. An observer far from a black hole watching someone fall toward it would see them slow down dramatically as they approach the event horizon, their clock ticking ever more slowly. But the infalling person experiences time normally, crossing the horizon in a finite time by their own measure. This relativity of time means that there is no universal now. Events that are simultaneous for one observer are not simultaneous for another moving differently. The order of events can even differ for different observers if the events are not causally connected. The universe does not have a single universal timeline, but rather a complex fabric of interwoven local times. For objects moving at ordinary speeds and in weak gravitational fields, time dilation effects are negligible, but they become significant for GPS satellites, particle accelerators, and astronomical observations. Time dilation is not a theoretical curiosity, but a practical reality that must be accounted for in modern technology and science. The flexibility of time challenges our intuitive understanding of reality. We perceive time as flowing uniformly, a backdrop against which events unfold. But relativity reveals that time is part of space-time, a dynamic fabric that bends, stretches, and varies from place to place. Time itself is woven into the structure of the cosmos. The universe may be curved space, can have geometry. It can be flat, like an infinite plane, positively curved, like the surface of a sphere, or negatively curved, like a saddle. The overall curvature of the universe is determined by its total energy density. If the density equals the critical density, space is flat. If it exceeds this value, space curves back on itself. If it is less, space curves outward. Measurements of the cosmic microwave background reveal that the universe is very nearly flat, within measurement precision. This does not mean space is a flat plane, but rather that parallel lines remain parallel, and the angles of triangles sum to exactly 180 degrees, just as they do in the flat geometry we learn in school. If the universe were positively curved, it would be finite but unbounded. Like the surface of a sphere, you could travel in one direction and eventually return to your starting point without ever encountering an edge. If negatively curved, space would be infinite and open, extending forever with an accelerating expansion. The flatness of the universe is another puzzle related to inflation. Without inflation, the universe would need to start with exactly the critical density to remain nearly flat today. Any small deviation would have grown over time, making the universe extremely curved by now. Inflation solves this by stretching space until any initial curvature becomes negligible. Even if space is globally flat, it can still be curved locally by mass and energy. The Sun curves space-time around it, creating the gravity that holds planets in orbit. Earth curves space-time slightly, affecting GPS satellites. Black holes curve space-time extremely. These local curvatures exist within the overall flat geometry of cosmic space. The possibility remains that the universe has curvature too small for us to detect. Perhaps on scales larger than the observable universe, space curves back on itself. We may inhabit a finite cosmos that wraps around, though we cannot see far enough to know. The true geometry of space beyond our horizon remains one of cosmology's open questions. Quantum fluctuations created structure. In the quantum realm, nothing is perfectly still. Even in a vacuum, particle pairs constantly pop into and out of existence. Energy fluctuates, and fields vary randomly. These quantum fluctuations are normally confined to microscopic scales, too small to notice in everyday life. But during cosmic inflation, something extraordinary happened. As space expanded exponentially, quantum fluctuations were stretched to enormous scales. Tiny variations in energy density at subatomic scales became fluctuations spanning light years, then galaxies, then superclusters. These stretched quantum fluctuations were frozen into the fabric of space, creating the seeds of all structure we see today. After inflation ended, these fluctuations became regions of slightly higher and lower density in the cosmic plasma. Gravity amplified the differences. Higher density regions attracted more matter and grew denser. Lower density regions lost matter and became voids. Over hundreds of millions of years, the densest regions collapsed to form the first stars and galaxies. The cosmic microwave background provides a snapshot of these fluctuations when the universe was only 380,000 years old. The tiny temperature variations we observe match perfectly with quantum fluctuations stretched by inflation. This agreement is powerful evidence that quantum mechanics operated at the birth of the cosmos. It is remarkable that quantum randomness, the inherent uncertainty at the smallest scales, shaped the largest structures in the universe. Every galaxy, every cluster, every void traces back to quantum fluctuations that existed when the universe was smaller than an atom. The arrangement of galaxies across the sky reflects quantum events at the moment of cosmic birth. This connection between the quantum and cosmic scales reveals a deep unity in physics. The same quantum mechanics that governs atoms and particles also governed the early universe. The randomness of quantum fluctuations, amplified by inflation, created the cosmic diversity we observe. Without quantum mechanics, the universe might have remained perfectly uniform, with no structure forming at all. Cosmic strings may thread through space. Some theories predict that the early universe underwent phase transitions as it cooled, similar to water freezing into ice. During these transitions, defects might have formed in the fabric of space-time, creating exotic structures called cosmic strings. These would be incredibly thin, perhaps narrower than a proton, but stretching across cosmic distances. Cosmic strings, if they exist, would have enormous tension and mass. A loop of cosmic string a few kilometers long could have the mass of Earth. They would warp space-time around them, creating detectable gravitational effects. Moving cosmic strings would produce gravitational waves, potentially observable by current or future detectors. Although cosmic strings have never been directly detected, astronomers have searched for their signatures. They would gravitationally lens background galaxies, creating distinctive double images. They might produce specific patterns in the cosmic microwave background. So far, no definitive evidence has emerged, placing limits on how common cosmic strings could be. Other topological defects might also exist. Domain walls are two-dimensional surfaces where different regions of space are in different quantum states. Monopoles are point-like defects carrying magnetic charge. Each type would have unique properties and observational signatures. Their existence depends on the details of physics in the extremely early universe. The search for cosmic strings and other defects continues, because they would provide a window into physics at extraordinarily high energies, far beyond what particle accelerators can reach. Detecting them would confirm aspects of grand unified theories or superstring theory, revealing how fundamental forces were unified in the early universe. Even if cosmic strings do not exist, the possibility illustrates how the fabric of space-time itself can have complex structure. Space is not a passive backdrop, but an active participant in cosmic evolution. Understanding its full nature, including possible defects and exotic structures, remains an ongoing challenge in theoretical cosmology. The cosmic web connects all galaxies. Galaxies are not randomly distributed through space. They form an intricate pattern called the cosmic web, a vast network of filaments, walls, and voids that extends across the universe. This structure reflects the distribution of matter in the early universe, amplified by billions of years of gravitational evolution. The densest regions of the cosmic web are galaxy clusters, containing hundreds or thousands of galaxies bound together by gravity. Between these clusters stretch filaments, elongated structures tracing the largest concentrations of matter. Where filaments intersect, superclusters form, the largest gravitationally bound structures known. Between the filaments lie cosmic voids, vast regions relatively empty of galaxies. These voids are not completely empty, but contain much less matter than average. Some voids are hundreds of millions of light-years across. Galaxies at the edges of voids tend to be brighter and younger, having gathered material from the void. The cosmic web is traced primarily by dark matter, which makes up most of the matter in the universe. Regular matter, the stuff of stars and gas, follows the gravitational potential wells created by dark matter. The visible galaxies we observe are like beads strung along invisible dark matter filaments. Simulations of structure formation reproduce the cosmic web remarkably well. Starting from the tiny fluctuations in the early universe and following gravitational dynamics forward in time, computers generate structures that match observations. The agreement validates our understanding of gravity and dark matter on cosmic scales. The cosmic web reveals the history of structure formation written across the sky. The patterns we observe today grew from subtle variations in density present when the universe was still smooth and uniform. Every filament and void tells a story of gravitational attraction and cosmic expansion, competing over billions of years. Baryon acoustic oscillations measure distance. In the early universe, before atoms formed, pressure waves moved through the hot plasma like sound waves through air. These waves were driven by the competition between gravity pulling matter together and radiation pressure pushing it apart. When atoms formed and the universe became transparent, these oscillations were frozen into the distribution of matter. The characteristic scale of these oscillations, about 500 million light-years today, is imprinted in the distribution of galaxies. Galaxies are slightly more likely to be separated by this distance than by other distances. This subtle excess in galaxy clustering is called the Baryon acoustic oscillation peak. Because we know the physical size of this scale from the physics of the early universe, we can use it as a standard ruler. By measuring how large this scale appears at different distances, astronomers can trace the expansion history of the universe. If the universe has expanded more, the ruler appears smaller. If less, it appears larger. Baryon acoustic oscillations provide an independent check on measurements of dark energy and the expansion rate. They complement other methods like supernovae observations. Multiple independent techniques give cosmologists confidence in their measurements and help reveal subtle effects that any single method might miss. Large galaxy surveys have mapped millions of galaxies to measure baryon acoustic oscillations with increasing precision. These surveys trace the cosmic web at different epochs, revealing how structure has grown and how the expansion rate has evolved. The results consistently support a universe dominated by dark energy. The ability to use sound waves from the early universe as cosmic rulers demonstrates the power of modern cosmology. Phenomena from the first few 100,000 years provide tools for mapping the universe billions of years later. The cosmos is interconnected across time and scale in ways that allow us to decode its history. Cosmic rays arrive from distant accelerators. Earth is constantly bombarded by cosmic rays, high-energy particles from space. Most are protons or atomic nuclei. Traveling at nearly the speed of light, they carry enormous energies, far greater than anything our particle accelerators can achieve. When they strike Earth's atmosphere, they create cascades of secondary particles that rain down to the surface. The origin of cosmic rays remains partially mysterious. Lower energy cosmic rays likely come from supernova remnants in our galaxy, where shock waves accelerate particles to high energies. But the highest energy cosmic rays, with energies exceeding 10 to the 20 electron volts, must come from beyond the Milky Way. No known mechanism in our galaxy can accelerate particles to such extremes. Candidate sources for ultra-high energy cosmic rays include active galactic nuclei, where supermassive black holes accelerate jets of material to relativistic speeds. Gamma-ray bursts, the most powerful explosions in the universe, might also produce them. Even more exotic sources, like the decay of super-heavy dark matter particles, have been proposed. Cosmic rays are difficult to trace back to their sources. Magnetic fields in space deflect charged particles, scrambling their trajectories. By the time they reach Earth, their directions no longer point back to their origin. Only the highest energy cosmic rays travel relatively straight, but these are extremely rare, perhaps 1 per square kilometer per century. Despite the challenges, cosmic ray detectors around the world monitor the sky constantly. Arrays of ground-based detectors spread over vast areas can reconstruct the energy and direction of incoming cosmic rays from the cascades they produce. Space-based detectors observe from above the atmosphere, catching particles before they interact. Cosmic rays represent a form of particle physics done by the universe itself, at energies we cannot reproduce in laboratories. Studying them probes both astrophysics, the sources and acceleration mechanisms, and particle physics, the behavior of matter at extreme energies. They are messengers from violent cosmic accelerators, carrying information about the most energetic phenomena in existence. Neutrinos pass through everything. Neutrinos are ghostly particles that barely interact with matter. Trillions pass through your body every second, coming from the sun, from cosmic rays, from reactors and accelerators, and from distant cosmic sources. Almost all pass through Earth completely unimpeded, as if our planet were not even there. Despite their elusiveness, neutrinos carry important information. They are produced in nuclear reactions, including those in the sun's core and in supernovae. Unlike light, neutrinos escape immediately from dense regions, carrying direct information about conditions deep inside stars and other cosmic sources. In 1987, neutrino detectors on Earth observed a burst of neutrinos from supernova 1987A in the Large Magellanic Cloud. These neutrinos arrived hours before the light, traveling unimpeded from the collapsing core, while light took time to diffuse through the star's outer layers. This detection confirmed theories of stellar collapse and opened the field of neutrino astronomy. Massive underground detectors, filled with water or other materials, catch rare neutrino interactions. When a neutrino occasionally collides with an atom, it produces charged particles that emit characteristic light. By detecting this light, physicists can reconstruct the neutrino's energy and direction, tracing it back to cosmic sources. Neutrinos come in three types or flavors, associated with electrons, muons, and tau particles. Remarkably, neutrinos oscillate between these flavors as they travel. This oscillation requires that neutrinos have mass, a property not included in the original standard model of particle physics. Measuring neutrino properties probes physics beyond our current theories. The cosmic neutrino background, analogous to the cosmic microwave background, should permeate space. These relic neutrinos decoupled from matter when the universe was just 1 second old, even earlier than the photons we observe. Detecting this neutrino background would provide a snapshot of the universe at an even younger age, though it remains beyond current technology. The Anthropic principle questions our existence. The Anthropic principle observes that the universe must be compatible with the existence of observers. This seems obvious, but leads to subtle implications. In its weak form, it simply notes that we should not be surprised to observe physical laws compatible with our existence, since we could not exist otherwise. The strong Anthropic principle suggests that the universe must have properties that allow observers to develop at some point. This raises questions about why the universe has the specific properties it does. If many universes exist with different properties, we naturally find ourselves in one of the rare ones compatible with life. Critics argue that the Anthropic principle is not explanatory. Saying we observe certain conditions because we could not exist otherwise does not explain why those conditions hold. It seems to substitute observational selection bias for genuine physical understanding. Yet defenders argue it provides a legitimate framework when combined with multiverse theories. In cosmology, anthropic reasoning is sometimes used to address fine-tuning problems. The small value of the cosmological constant, the specific strengths of forces, and other apparently special features might not require fundamental explanations if a multiverse exists. We simply happen to inhabit one of the universes where conditions permit complexity and life. However, relying on anthropic reasoning can be dangerous. It might discourage searching for deeper physical explanations. Before invoking anthropic selection, physicists prefer to exhaust other possibilities. The principle should be a last resort, not a first response to unexplained features of the universe. The anthropic principle connects cosmology to philosophy and even theology. It raises questions about the meaning of physical laws, the nature of existence, and our place in the cosmos. Whether it represents profound insight or circular reasoning remains debated, but it highlights how cosmology touches the deepest questions we can ask. Cosmic expansion will eventually isolate galaxies. As dark energy drives the accelerating expansion, distant galaxies move away from us ever faster. Eventually, galaxies beyond our local group will recede faster than light can travel through the expanding space between us. This does not violate relativity. Space itself can expand at any rate, but it means those galaxies will disappear beyond our cosmic horizon. In about 150 billion years, galaxies outside our local group will have receded so far that their light can no longer reach us. The observable universe will shrink to include only the merged remnant of the Milky Way and Andromeda galaxies, plus the small satellite galaxies bound to them. The rest of the cosmos will be invisible. Future astronomers in that distant era, if they exist, will see a very different sky than we do. With only one galaxy visible, they might conclude they live in an island universe surrounded by eternal emptiness. They would have no way to know that countless other galaxies exist beyond their horizon. forever unreachable. This raises a sobering question. What are we missing? Are there cosmic features already beyond our horizon that we can never observe? The universe might be far larger and more complex than the portion accessible to us. Our observable universe might be as limited relative to the full cosmos as that far future view will be. The isolation of galaxies is one scenario for the far future, assuming dark energy remains constant. Other possibilities exist. If dark energy grows stronger, it could lead to a big rip, tearing apart galaxies, stars, and eventually atoms. If it weakens or reverses, gravity might eventually halt expansion and cause collapse. The ultimate fate of cosmic expansion remains uncertain, depending on the nature of dark energy, which we do not fully understand. Observations continue to refine our knowledge, but dark energy might evolve in unpredictable ways. The universe's future is written in the properties of this mysterious component, and we are still learning to read the text. The heat death of the universe. If expansion continues indefinitely, the universe will eventually reach a state of maximum entropy. Stars will burn out, black holes will evaporate, and all energy will be spread uniformly through an ever-expanding space. This final state is called the heat death of the universe, though cold death might be more accurate, as temperatures approach absolute zero. Long before heat death, the universe will become a very different place. In 1 trillion years, most stars will have exhausted their fuel. The universe will be populated by stellar remnants, white dwarfs, neutron stars, and black holes, along with wandering planets and cold gas. New star formation will have ceased as available hydrogen is used up. After 10 to the 14 years, even the longest-lived stars, tiny red dwarfs, will have burned out. The universe will be dark except for occasional flashes from colliding stellar remnants. Black holes will dominate, slowly growing by consuming any matter that wanders too close. The cosmos will be cold, dark, and nearly changeless. Black holes eventually evaporate through Hawking radiation, though the process is unimaginably slow. A black hole with the mass of the Sun would take 10 to the 67 years to evaporate completely. Supermassive black holes at galactic centers would last until 10 to the 100 years or longer, but even they must eventually fade. After black holes evaporate, the universe will contain only a thin soup of elementary particles and radiation, spread over exponentially expanding space. Entropy will be at maximum, with no gradients to drive change, no structure, no complexity. Time will still pass, but nothing will happen. The universe will have reached thermal equilibrium at near absolute zero. Yet even this might not be the end. Quantum mechanics allows unlikely events to eventually occur if you wait long enough. Over timescales of 10 to the 10 to the 50 years or more, quantum fluctuations might spontaneously create new structures, perhaps even new universes. The far future remains speculative because the timescales involved exceed human comprehension. Boltzmann brain's challenge, probability. In the far future, random quantum fluctuations might occasionally create organized structures purely by chance. Given infinite time, any configuration of particles allowed by physics will eventually occur. This includes the spontaneous appearance of brains, complete with false memories, that exist briefly before dispersing. These hypothetical Boltzmann brains pose a paradox. If the universe exists for an infinite or near-infinite time, vastly more brains will form by random fluctuation than by evolution. If you assume you are a typical observer, you should expect to be a Boltzmann brain rather than a biological one. Yet you seem not to be, having consistent memories and experiences. This paradox is used to constrain cosmological models. Theories that predict infinitely many Boltzmann brains are considered problematic because they make our existence as evolved observers extremely unlikely. The Boltzmann brain problem influences debates about the ultimate fate of the universe and the nature of dark energy. One resolution might be that the universe does not last forever. If expansion eventually leads to a big rip, or if dark energy decays, the era of random fluctuations might never arrive. Alternatively, our understanding of quantum mechanics in the far future might be incomplete, preventing the formation of Boltzmann brains. The concept illustrates how cosmology intersects with deep questions about consciousness, probability, and the nature of observation. It forces us to think carefully about what it means to be a typical observer and whether our theories make our own existence likely or unlikely. Boltzmann brains are more a thought experiment than a practical concern. The timescales involved are so vast as to be almost meaningless. Yet the paradox serves as a useful tool for evaluating cosmological theories, ensuring they make predictions consistent with our existence as observers who have evolved in a arrayed universe with real history. The problem of time in quantum gravity. Unifying quantum mechanics with general relativity remains one of the greatest challenges in physics. One issue is the problem of time. In quantum mechanics, time is a fixed background against which events unfold. In general relativity, time is part of spacetime, dynamical and affected by matter and energy. In quantum gravity, there is no preferred time coordinate. The theory must be timeless in a certain sense, describing correlations between physical quantities without reference to an external clock. This makes it difficult to formulate quantum mechanics in the usual way, which relies on states evolving in time. Some approaches to quantum gravity, like loop quantum gravity and string theory, handle time differently. Wheeler-DeWitt equation describes the quantum state of the universe, but contains no time parameter at all. Time emerges only as a concept within certain solutions, not as a fundamental feature of the theory. This suggests that time itself might be an emergent phenomenon, not fundamental but arising from deeper structures. Just as temperature emerges from the motion of molecules, time might emerge from quantum entanglement or other fundamental quantum properties. Our perception of time's flow might reflect something about our place within the universe rather than a fundamental feature of reality. The problem of time connects to the nature of the Big Bang. If time itself began at the Big Bang, asking what happened before becomes meaningless. But if time is emergent, perhaps something existed before, in some more fundamental sense. These questions push at the limits of both physics and language. Resolving the problem of time is essential for understanding the quantum nature of the early universe, black hole interiors, and the ultimate structure of spacetime. Progress requires new mathematical tools and possibly new conceptual frameworks. The nature of time remains one of the deepest mysteries in cosmology and physics. String theory proposes extra dimensions. String theory attempts to unify all forces and particles by proposing that fundamental constituents of reality are not point particles, but tiny vibrating strings. Different vibration modes correspond to different particles, electrons, quarks, photons, and others. This elegant idea requires extra spatial dimensions beyond the three we observe. In most versions of string theory, the universe has 9 spatial dimensions plus 1 time dimension, for a total of 10. We observe only 3 spatial dimensions because the extra 6 are compactified, curled up so small that we cannot detect them. The specific geometry of these hidden dimensions determines the properties of particles and forces in our 3-dimensional world. The landscape of possible compactifications is vast, perhaps 10 to the 500 different possibilities, each corresponding to a different vacuum state with different physical laws. This enormous number troubles some physicists, as it seems to eliminate the theory's predictive power. If anything is possible somewhere in the landscape, how can we test the theory? Proponents argue that string theory remains viable, even with a large landscape. If the multiverse is real, different regions might realize different vacua, and anthropic reasoning explains why we observe the particular one we do. The theory might predict statistical properties of universes rather than unique values for all constants. String theory has led to important insights in mathematics and theoretical physics, even though experimental confirmation remains elusive. The energies needed to directly observe strings are far beyond what particle accelerators can reach. Indirect evidence might come from cosmology, such as signatures in the cosmic microwave background or gravitational wave observations. Extra dimensions, if they exist, would fundamentally change our understanding of space. The geometry of hidden dimensions could influence dark matter, dark energy, and the values of physical constants. Though speculative, string theory represents humanity's most ambitious attempt to construct a complete theory of everything, unifying all of physics in a single framework. Loop quantum gravity quantizes space. An alternative approach to quantum gravity is loop quantum gravity, which does not require extra dimensions or strings. Instead, it applies quantum mechanics directly to space-time itself, treating geometry as a quantum entity. Space, at the smallest scales, becomes discrete, composed of fundamental units. In loop quantum gravity, space-time has a granular structure at the Planck scale, around 10 to the minus 35 meters. This quantum foam of discrete spatial elements replaces the smooth continuum of classical space-time. Area and volume become quantized, coming in discrete chunks rather than varying continuously. This quantization of space has implications for cosmology. The infinite density singularity predicted by general relativity at the Big Bang might be avoided. When matter is compressed to the Planck density, quantum effects become important and might prevent further collapse. The Big Bang could be replaced by a big bounce, with our universe emerging from the collapse of a previous one. Loop quantum gravity makes specific predictions that differ from general relativity in extreme conditions. These predictions might be testable through observations of the cosmic microwave background or in the quantum properties of black holes. Finding distinctive signatures would provide evidence for this approach to quantum gravity. The theory remains incomplete, with many technical challenges unresolved. Unlike string theory, loop quantum gravity does not yet incorporate matter and forces in a fully consistent way. It focuses on quantizing gravity first, hoping to add other physics later. This bottom-up approach contrasts with string theory's top-down unification. Whether loop quantum gravity or string theory or some other approach will ultimately succeed remains unknown. Both address the problem of quantum gravity from different perspectives, and both have strengths and weaknesses. The true theory might incorporate elements from multiple approaches, or it might be something entirely different that we have not yet conceived. The Planck scale defines limits. At extremely small scales, around 10 to the minus 35 meters and 10 to the minus 43 seconds, quantum gravity effects become dominant. This is the Planck scale, defined by combining the fundamental constants of quantum mechanics, gravity, and relativity. At the Planck scale, space and time themselves become uncertain, fluctuating wildly. Below the Planck length, the concept of distance becomes ill-defined. Quantum fluctuations in space-time geometry become so severe that the notion of a smooth continuum breaks down. Similarly, below the Planck time, the sequence of cause and effect becomes ambiguous. These scales represent a fundamental limit to how finely we can probe spacetime. The Planck energy, about 10 to the 19 giga-electron volts, is the energy at which quantum gravity matters. This is far beyond what particle accelerators can reach. The Large Hadron Collider achieves energies around 10 tera-electron volts, many orders of magnitude below the Planck energy. Direct experimental tests of quantum gravity remain impossible with current technology. However, the early universe reached Planck scale conditions. For a brief moment, perhaps 10 to the minus 43 seconds after the Big Bang, the universe was so hot and dense that quantum gravity determined its behavior. Studying the cosmic microwave background and other cosmological observations might reveal indirect signatures of Planck scale physics. Black holes also involve Planck scale physics. Near their singularities, densities and curvatures become extreme. Understanding what happens requires quantum gravity. The information paradox, concerning whether information is lost when matter falls into a black hole, touches on fundamental issues about quantum mechanics and gravity at the Planck scale. The Planck scale defines the ultimate limits of our physical theories. Below these scales, new physics must emerge, though we do not yet know what form it takes. Reaching this frontier intellectually, through theory and indirect observation, represents one of the great quests of modern physics. The Planck scale is the door to the deepest level of physical reality. Cosmic acceleration was a complete surprise. Before 1998, most cosmologists expected the universe's expansion to be slowing down. Gravity should pull galaxies together, gradually breaking the expansion left over from the Big Bang. The question was whether there was enough matter to eventually halt expansion completely, or whether expansion would continue forever, but at an ever-decreasing rate. Two teams of astronomers set out to measure the deceleration of the universe by observing distant supernovae. Type Ia supernovae serve as standard candles because their intrinsic brightness is known. By comparing apparent brightness to known intrinsic brightness, astronomers can determine distance. Combined with redshift, this reveals the expansion history. The results shocked everyone. Distant supernovae were fainter than expected, meaning they were farther away than calculations predicted. The universe had not been decelerating, it had been accelerating. Expansion was speeding up, not slowing down. This contradicted decades of theoretical expectation and observational planning. The discovery implied that some unknown energy was driving acceleration. This energy, dubbed dark energy, must have negative pressure, a property that causes repulsion rather than attraction. The simplest candidate was Einstein's cosmological constant, but other possibilities existed. Regardless of its nature, dark energy was the dominant component of the universe's energy budget. The discovery earned the leaders of the two teams the Nobel Prize in Physics. It transformed cosmology, opening new questions about the nature of dark energy, the ultimate fate of the universe, and the completeness of our physical theories. An observation intended to measure deceleration revealed acceleration, reminding us that the universe can surprise us completely. Since then, many observations have confirmed cosmic acceleration. Different methods and larger data sets have refined the measurements but not changed the fundamental conclusion. Dark energy is real. Its effects are measurable, and it dominates the universe. Yet we still do not understand what it is, making it one of the greatest mysteries in all of science. The cosmic microwave background is nearly perfect. The cosmic microwave background radiation is remarkably uniform across the sky. Its temperature varies by only about 1 part in 100,000 from place to place. This uniformity posed a problem for early Big Bang models. How did regions of space that could never have communicated reach the same temperature? Inflation solved this horizon problem. Before inflation, the entire observable universe was small enough for all regions to reach thermal equilibrium. Then inflation stretched these regions apart faster than light could travel between them. They retained their uniform temperature, even though they became causally disconnected. The tiny variations that do exist in the cosmic microwave background are incredibly important. These fluctuations represent the seeds of all structure. Regions slightly warmer than average were slightly denser and eventually collapsed to form galaxies. Regions slightly cooler became voids. The pattern of fluctuations encodes information about the early universe. Satellites like COBE, WMAP, and Planck have mapped the cosmic microwave background with increasing precision. The data reveals the universe's age, composition, geometry, and the properties of the initial fluctuations. The cosmic microwave background is the most precisely measured cosmological dataset we have, constraining theories with remarkable accuracy. The temperature of the cosmic microwave background today is 2.725 degrees above absolute zero. This precise value results from the expansion of the universe. As space expanded, the radiation stretched to longer wavelengths, cooling from thousands of degrees to just a few degrees over billions of years. Looking at the cosmic microwave background is like looking at a baby picture of the universe. We see it as it was at 380,000 years old, just emerging from its opaque infancy. The patterns in this ancient light tell the story of how the universe began, how it evolved, and where it is going. Few scientific datasets contain so much information in such a simple image. Primordial. Nucleosynthesis predicted light elements. One of the great triumphs of Big Bang theory is its prediction of the abundance of light elements. In the first few minutes after the Big Bang, nuclear fusion created specific ratios of hydrogen, helium, and trace amounts of other light elements. These predictions match observations with remarkable accuracy. The theory predicted that about 25% of ordinary matter by mass should be helium, with most of the rest being hydrogen. When astronomers measured the helium abundance in ancient stars and gas clouds, they found exactly this ratio. No other theory could explain why helium is so abundant throughout the universe. Deuterium, a heavy form of hydrogen with one proton and one neutron, is also predicted by Big Bang nucleosynthesis. Its abundance is more sensitive to conditions in the early universe, particularly the density of ordinary matter. Measurements of deuterium abundance in distant gas clouds provide constraints on cosmological parameters. Lithium presents a small puzzle. The predicted abundance is slightly higher than what astronomers observe in the oldest stars. This lithium problem might indicate that we do not fully understand stellar evolution, or it might point to new physics in the early universe. Despite this discrepancy, the overall agreement between prediction and observation is impressive. The success of primordial nucleosynthesis provides strong support for the Big Bang model. The abundances were set in the first 3 minutes, yet they match observations of objects billions of years old across vast distances. This consistency shows that the early universe really was hot and dense, cooling and expanding, as theory describes. No other theory explains the observed abundances of light elements. Alternative models like steady-state cosmology cannot account for why helium is so common. Big Bang nucleosynthesis remains one of the strongest pieces of evidence that the universe had a hot beginning, a moment when nuclear fusion occurred throughout all of space. The cosmic dawn lit up the universe. After hundreds of millions of years of darkness, the first stars ignited, bringing light back to the universe. This epoch, called cosmic dawn, marks the beginning of the current era. The first stars were massive, hot, and short-lived, nothing like the Sun. They formed from pure hydrogen and helium, with no heavier elements. These population 3 stars, as they are called, were perhaps 100 times more massive than the Sun. They burned brilliantly but briefly, exhausting their fuel in just a few million years before exploding as supernovae. Their death scattered the first heavy elements into space: carbon, oxygen, silicon, iron, enriching the gas from which later stars would form. The ultraviolet light from these first stars began ionizing the hydrogen gas that filled space. Over hundreds of millions of years, bubbles of ionized gas grew around galaxies and eventually merged, reionizing the entire universe. This epoch of reionization transformed the cosmos from neutral to ionized, as it had been before recombination. Observing the first stars directly is challenging because they are extremely distant and faint. The James Webb Space Telescope is designed to peer back to this era, detecting the infrared light from these ancient objects. Early results are already revealing galaxies brighter and more massive than expected at early times. The chemical signatures of population 3 stars might be found in the oldest surviving stars in our galaxy. These ancient stars, formed soon after the first generation, should contain traces of the elements produced by population 3 supernovae. Astronomers search for stars with unusual chemical compositions that might reveal the nature of the first stellar generation. Cosmic dawn represents the universe's transition from simplicity to complexity. Before, there were only hydrogen and helium drifting through, expanding space. After, there were stars, galaxies, heavy elements, and eventually planets and life. The first stars lit more than the universe. They lit the path toward everything that would follow. Supermassive black holes grew quickly. At the centers of most large galaxies lie supermassive black holes, with masses millions to billions of times that of the Sun. These monsters influence their host galaxies through gravity and through powerful jets of energy they emit when consuming matter. But their origin is mysterious, especially how they grew so large so quickly. Observations reveal supermassive black holes already in place when the universe was less than 1 billion years old, just 7% of its current age. How did they accumulate so much mass so rapidly? Starting from stellar mass black holes and growing by accretion seems too slow to reach billions of solar masses in such short time. Several theories attempt to explain rapid black hole growth. Perhaps the first black holes formed directly from collapsing gas clouds, starting with thousands or even millions of solar masses. Perhaps they grew by merging with each other as galaxies collided and merged. Perhaps they accreted matter at super Eddington rates, exceeding theoretical limits. The relationship between black holes and their host galaxies suggests they grew together. More massive galaxies host more massive black holes, with a tight correlation. Black holes influence galaxy evolution through feedback. Where jets and winds, they produce heat or expel gas, regulating star formation. Gravitational wave observations might reveal the history of black hole mergers. As supermassive black holes from colliding galaxies spiral together, they emit gravitational waves at frequencies detectable by future space-based observatories. These observations would trace black hole growth through cosmic time. The rapid growth of supermassive black holes remains an active area of research. It connects questions about the first stars, the formation of the first galaxies, and the role of black holes in cosmic structure. Understanding how these monsters formed and grew so quickly is essential to understanding how the universe evolved from its early simplicity to its current complexity. Galaxy mergers shape cosmic evolution. Galaxies are not isolated islands, but interactive systems that frequently collide and merge. These collisions can trigger intense bursts of star formation, feed supermassive black holes, and transform galaxy shapes. Mergers are a key process in the hierarchical growth of structure, building large galaxies from smaller ones. When galaxies collide, their stars rarely collide because the distances between stars are vast. But the gas clouds do collide, shocking and compressing them. This triggers collapse and rapid star formation, creating brilliant starburst galaxies. Some of the most luminous galaxies in the universe are experiencing merger-driven starbursts. Mergers also funnel gas toward galactic centers, feeding supermassive black holes. As black holes consume this material, they can become active galactic nuclei or quasars, shining brighter than their entire host galaxy. Many quasars are found in merging or recently merged galaxies, supporting the connection between mergers and black hole activity. The shapes of galaxies reveal their merger history. Elliptical galaxies are thought to result from major mergers between spiral galaxies. The collision disrupts the delicate spiral structure, scrambling stellar orbits and creating a smooth, featureless ellipse. Irregular galaxies often show signs of recent interactions or mergers. Our own Milky Way is currently consuming several small satellite galaxies and will eventually merge with Andromeda. In about 4 billion years, these two galaxies will collide in a slow-motion dance lasting billions of years. The result will be a giant elliptical galaxy, sometimes called Milkomeda, with the Sun and its planets flung to a new location within it. Observing galaxies at different distances and thus different cosmic times reveals how merger rates have changed. Mergers were more common in the early universe when galaxies were closer together. As expansion increased distances between galaxies, major mergers became less frequent. The universe's structure reflects billions of years of gravitational interactions. Quasars are the brightest objects. Quasars are the most luminous, persistent sources of light in the universe. These extremely distant objects shine with the power of trillions of suns. So bright, they outshine entire galaxies. For decades after their discovery in the 1960s, their nature remained mysterious. They looked like stars but had enormous redshifts, placing them billions of light years away. We now understand that quasars are powered by supermassive black holes actively consuming matter. As gas spirals into the black hole, it forms an accretion disk heated to millions of degrees. The disk shines brilliantly across the electromagnetic spectrum. Jets of particles traveling near the speed of light shoot outward from the poles, extending for thousands of light years. Quasars were more common in the early universe when galaxies contained abundant gas to fuel black hole growth. Today, most supermassive black holes are quiescent, starved of fuel. Our own galaxy's black hole is relatively quiet, consuming material only sporadically. But in the distant past, when the universe was denser, quasars blazed throughout space. The light from quasars has traveled for billions of years to reach us. We see them as they were when the universe was young. Studying quasars provides information about conditions in the early universe, including the abundance of elements, the ionization state of gas, and the distribution of matter along the line of sight. Quasar spectra show absorption lines from intervening gas clouds. As quasar light travels toward us, it passes through cosmic web filaments, absorbing specific wavelengths. These absorption lines create a pattern called the Lyman alpha forest, revealing the distribution of hydrogen gas across cosmic time and distance. Though individual quasars are transient on cosmic timescales, perhaps lasting only 10 to 100 million years before exhausting their fuel supply, they represent an important phase in galaxy evolution. The energy they inject into their surroundings can heat gas, preventing it from forming stars. and thus regulate galaxy growth. Gamma-ray bursts are cosmic catastrophes. Gamma-ray bursts are the brightest explosions in the universe since the Big Bang. For a few seconds to a few minutes, they emit more energy in gamma rays than the Sun will emit in its entire lifetime. They are so bright that despite occurring in distant galaxies, they are visible across the universe. These bursts come in two main types. Short bursts, lasting less than 2 seconds, are thought to result from colliding neutron stars or a neutron star merging with a black hole. Long bursts, lasting longer than 2 seconds, come from the collapse of extremely massive stars into black holes, a type of supernova called a hypernova or collapsar. When a massive star collapses, it can form a rapidly rotating black hole. Matter falling toward the black hole forms an accretion disk, and powerful jets shoot out along the rotation axis at nearly the speed of light. If Earth lies in the path of one of these jets, we observe a gamma-ray burst. The emission is beamed, like a lighthouse, so we see only a fraction of the bursts that occur. Gamma-ray bursts release as much energy in seconds as a typical galaxy does in years. If one occurred in our galaxy and pointed at Earth, it could be catastrophic, potentially stripping away the ozone layer and exposing the surface to harmful radiation. Fortunately, they are rare in any given galaxy and less likely to point our way. The afterglow of a gamma-ray burst can last for days or weeks as the blast wave plows through surrounding material. This afterglow is visible in X-rays, optical light, and radio waves, allowing astronomers to locate the burst's host galaxy and study the environment. Some gamma-ray bursts are among the most distant objects ever observed. In 2017, gravitational waves from merging neutron stars were detected along with a gamma-ray burst, confirming the connection. This event opened a new era of multi-messenger astronomy, combining gravitational waves and light to study cosmic catastrophes. Future detections will reveal details about neutron star composition and the creation of heavy elements. The Fermi paradox questions alien life. Given the vast number of stars and planets in the universe, it seems likely that life should be common, yet we see no evidence of advanced civilizations anywhere. This is the Fermi paradox, named after physicist Enrico Fermi, who asked, "Where is everybody?" The silence of the cosmos is puzzling, given the apparent abundance of opportunities for life. Several explanations have been proposed. Perhaps life is rare, requiring a highly specific set of conditions. Perhaps intelligence is rare, or technological civilizations are rare. Perhaps advanced civilizations exist but are difficult to detect, using communication methods we do not recognize, or simply not attempting to communicate. The Great Filter hypothesis suggests that there is some step in the evolution from non-life to expanding civilization that is extremely unlikely. This filter could be behind us. Perhaps the origin of life itself is incredibly rare, making us one of the few successes. Or it could be ahead of us, meaning civilizations typically destroy themselves before reaching the stars. Another possibility is that space is too vast for civilizations to interact. The distances between stars are enormous, and the timescales of civilization might be brief compared to cosmic time. Civilizations might arise, flourish, and vanish without ever encountering one another, passing like ships in the night across the galaxy. The zoo hypothesis suggests that advanced civilizations exist, but deliberately avoid contact with less developed ones like us. Or perhaps they exist in forms so different from biological life that we do not recognize them. They might have transitioned to artificial intelligence or exist in virtual realities, leaving no observable trace. The question touches on cosmology because the age and size of the universe set the stage for life. The universe has existed for billions of years, long enough for countless opportunities for life to arise. Yet the vast spaces between stars may ensure that civilizations remain isolated. The Fermi paradox reminds us that despite all we know about the cosmos, we do not yet know whether we are alone. The universe might be a simulation. Some scientists and philosophers have speculated that our universe might be a simulation, a computer program run by a more advanced civilization. This idea, while speculative, raises interesting questions about the nature of reality and the limits of what we can know about the cosmos. The argument runs as follows. If it is possible to simulate conscious beings in a computer, then advanced civilizations might run many such simulations. If there are vastly more simulated universes than real ones, then statistically, we are more likely to be in a simulation than in base reality. Evidence for the simulation hypothesis is difficult to imagine. If the simulation is perfect, we could never detect it from within. But perhaps there are glitches or computational shortcuts that would leave signatures. Some have suggested that Planck-scale physics represents a kind of pixelation of reality, though this is highly speculative. Critics argue that the simulation hypothesis is unfalsifiable and thus not scientific. If no observation could ever confirm or refute it, then it lies outside the realm of science. Others point out logical problems with the argument, such as the assumption that consciousness can be simulated or that computing power could ever be sufficient. From a cosmological perspective, the simulation hypothesis does not change much. Even if true, we would still need to understand the laws of our simulated universe, which appear to be the laws of physics we observe. Science would proceed exactly as it does, uncovering the rules of the simulation. The simulation hypothesis is more philosophy than cosmology, but it illustrates how cosmological questions bleed into metaphysics. What is real? What is the nature of existence? These questions have fascinated humans for millennia, and cosmology, by revealing the vast scope and strange properties of the universe, continues to provoke them. Dark matter remains invisible. Despite comprising 27% of the universe's mass-energy content, dark matter has never been directly detected. Its existence is inferred entirely from gravitational effects on visible matter. Galaxies rotate too fast, galaxy clusters contain too much mass, and gravitational lensing reveals more matter than we can see. Multiple candidates for dark matter particles have been proposed. WIMPs, weakly interacting massive particles, would have been produced in the early universe and would interact occasionally with ordinary matter. Axions are much lighter particles predicted by some theories. Sterile neutrinos are heavier cousins of ordinary neutrinos that interact only gravitationally. Experiments deep underground attempt to detect dark matter particles colliding with ordinary atoms. These detectors are shielded from cosmic rays and designed to catch the rare interactions of dark matter with atomic nuclei. Despite decades of searching and increasing sensitivity, no definitive detection has been made. Particle accelerators, like the Large Hadron Collider, search for dark matter by creating it in collisions. If dark matter is produced, it would carry away energy and momentum, leaving a signature of missing energy in the detector. Again, despite extensive searches, no clear signal has emerged. Some researchers have proposed modified theories of gravity to explain observations without dark matter. These theories, collectively called MOND for modified Newtonian dynamics, adjust the laws of gravity on large scales. While MOND can explain galaxy rotation curves, it struggles with galaxy clusters and the cosmic microwave background. The mystery of dark matter is humbling. We live in a universe where most of the matter is invisible and unknown to us. Everything we have ever seen or touched, all the elements in the periodic table, all the matter on Earth and in stars, represents less than 20% of the matter in the universe. The rest remains hidden, a vast invisible ocean we have barely begun to explore. The universe is isotropic and homogeneous. On the largest scales, the universe looks the same in all directions and at all locations. This property, called isotropy and homogeneity, is the foundation of modern cosmology. The cosmological principle asserts that Earth occupies no special place in the universe. Observers anywhere would see roughly the same cosmic environment. Isotropy means the universe looks the same in every direction. The cosmic microwave background has nearly uniform temperature across the sky, and the distribution of galaxies appears roughly equal in all directions. This symmetry suggests that the universe does not have a preferred direction or orientation. Homogeneity means the universe looks the same from any location on large scales. While galaxies cluster locally, when averaged over hundreds of millions of light-years, the density of matter is roughly constant. This implies there is no cosmic center or edge, at least not within the observable universe. These properties are not exact on small scales. Locally, matter clumps into galaxies, clusters, and the cosmic web. But when you zoom out, these irregularities average out, like how a rough surface appears smooth from a distance. The cosmological principle applies only when considering volumes large enough to average over local structure. Observations confirm isotropy and homogeneity remarkably well. Galaxy surveys show that the large-scale distribution of matter becomes more uniform as you look at larger volumes. The cosmic microwave background is uniform to 1 part in 100,000. These observations validate the cosmological principle and the models built upon it. The cosmological principle allows scientists to model the universe as a whole. Without it, cosmology would be vastly more complicated, potentially requiring different physics at different locations. The principle reduces the universe's description to a few parameters like expansion rate, density, and curvature, making cosmology tractable. Cosmic inflation solves multiple problems. Inflation theory solves several puzzles that plagued earlier versions of Big Bang cosmology. In addition to the horizon and flatness problems, inflation explains why we do not observe certain exotic relics that theories predict should have been created in the early universe, like magnetic monopoles. Grand unified theories predict that magnetic monopoles, particles with a single magnetic pole, should have been copiously produced in the early universe, yet we have never observed one. Inflation solves this monopole problem by diluting their density. If monopoles formed before inflation, the exponential expansion would spread them so far apart that we would be unlikely to encounter one. Inflation also explains the origin of structure. The quantum fluctuations stretched by inflation provide the seeds for galaxy formation. Without some mechanism to create these initial perturbations, the universe might have remained perfectly smooth, with no galaxies, stars, or planets ever forming. Inflation turns quantum uncertainty into cosmic structure. The theory makes testable predictions. It predicts the spectrum of fluctuations in the cosmic microwave background, specifically that the fluctuations should be nearly scale invariant, meaning similar at all scales. Observations confirm this prediction remarkably well. It also predicts primordial gravitational waves that might be detectable. Different inflationary models make different predictions about details like the exact shape of the fluctuation spectrum and the amplitude of gravitational waves. As observations improve, they constrain which inflationary models are viable. Some models have been ruled out, while others remain consistent with all data. Despite its successes, inflation is not without problems. We do not know what field drove inflation, or why it started and stopped when it did. The fine-tuning required to make inflation work raises questions. Some researchers pursue alternatives, like bouncing cosmologies, where the universe contracts and then rebounds. But inflation remains the leading framework for understanding the early universe. The observable universe will change. What we can observe is limited by the cosmic horizon, the distance from which light has had time to reach us. As time passes, this horizon grows, allowing us to see farther into space and thus farther back in time. But cosmic acceleration complicates this picture in surprising ways. Currently, the observable universe grows as light from more distant regions arrives, but galaxies beyond a certain distance are receding faster than light can travel through expanding space. We can see these galaxies now because the light we observe was emitted long ago when they were closer, but they are now beyond our event horizon and will never be visible again. In the far future, the observable universe will actually shrink in some sense. Distant galaxies will cross beyond the event horizon and disappear. Light they emit now will never reach us because the expansion carries them away faster than light can close the distance. The universe beyond a few billion light years will gradually fade from view. This means there are objects we can see today, but whose present state we will never observe. Their current condition is forever beyond our knowledge. The universe contains regions we can see into the past, but not the future. The event horizon imposes a fundamental limit on what we can know. Future astronomers, billions of years from now, will face a very different, observable universe than we do. If they tried to reconstruct cosmic history from their observations alone, they might reach different conclusions than we do. They might not observe the cosmic microwave background, as it will have redshifted to undetectably long wavelengths. This raises a philosophical question. What are we missing now? Are there features of the universe that were observable in the past but no longer? Has the evidence for important cosmic phenomena already disappeared beyond our horizon? The changing observable universe reminds us that our view is constrained by our place in space and time. The vacuum has energy. Empty space is not truly empty. Quantum field theory predicts that the vacuum is filled with quantum fluctuations, virtual particles that pop into and out of existence. These fluctuations give the vacuum an energy density, though calculating its exact value remains problematic. This vacuum energy should gravitate, affecting the expansion of the universe. In fact, vacuum energy is equivalent to Einstein's cosmological constant. A positive vacuum energy causes expansion to accelerate, pushing the universe apart. This is the simplest explanation for dark energy, identifying it with the energy of empty space itself. The Casimir effect provides experimental evidence for vacuum energy. Two uncharged metal plates, placed close together in a vacuum, experience an attractive force. This happens because virtual particles with wavelengths larger than the gap between the plates are excluded, creating an imbalance in vacuum energy that pushes the plates together. If vacuum energy is the explanation for dark energy, it raises questions about why its value is so small. Naive calculations predict a vacuum energy density vastly larger than observed. This is the cosmological constant problem, one of the most significant unsolved problems in theoretical physics. Some theories suggest that vacuum energy might change over time or vary from place to place. If dark energy is not a simple cosmological constant but rather a dynamical field, its density could evolve. Observations are testing whether dark energy remains constant or changes, with current data consistent with a constant. The concept of vacuum energy blurs the line between nothing and something. Empty space has structure and properties. It can carry energy and affect the evolution of the entire universe. The vacuum is not a backdrop, but an active component of reality, influencing everything from particle physics to cosmic expansion. our place in cosmic time. We exist at a special moment in cosmic history. The universe is old enough for complex structures like galaxies, stars, and planets to have formed, but young enough that stars still shine brightly. In the far future, the universe will be very different, darker and more isolated. If we had emerged earlier, heavy elements might have been too scarce for rocky planets like Earth to form. The first few billion years of cosmic history saw supernova gradually enriching the universe with carbon, oxygen, silicon, and iron. Only after several generations of stars died could planets capable of supporting life form. If we emerge much later, the view of the cosmos will be impoverished. In trillions of years, most stars will have burned out, and distant galaxies will have disappeared beyond the cosmic horizon. Future civilizations, if any exist, might not be able to discover the Big Bang or measure cosmic expansion, as the evidence will have faded. We are fortunate to live when the cosmic microwave background is still observable, when stars fill the galaxy, and when expansion can be measured from galaxy redshifts. Our place in cosmic time allows us to reconstruct the universe's history and predict its future. We can observe both the afterglow of the Big Bang and the acceleration toward an isolated future. This perspective instills both humility and urgency. Humility, because we are cosmically fortunate, existing at a time when the universe reveals its secrets. Urgency, because the window is closing. In cosmic terms, the era of abundant evidence is brief. We happen to exist during it, able to read the story written in starlight. Our place in cosmic time is neither central nor special in absolute terms, but it is special in that we can observe and understand. The universe has become conscious of itself through us, able to reflect on its own existence. For this brief moment in cosmic history, matter has arranged itself into forms capable of comprehending the whole. And so our journey through the cosmos comes to rest. We have traveled together through the deepest reaches of time and space, from the first instant of the Big Bang to the distant heat death of the universe. From quantum fluctuations smaller than atoms to structures spanning billions of light years, from the familiar stars above to the invisible dark matter and energy that dominate existence. The cosmos is vast beyond imagining, ancient beyond comprehension. It operates on scales of size and time that dwarf human experience. Yet, we are part of it, made from atoms, forged in stellar furnaces, shaped by the same forces that govern galaxies. We are the universe, examining itself, brief flickers of consciousness in an ocean of matter and energy. Many mysteries remain unsolved. What is dark matter? What is dark energy? What happened before the Big Bang, if anything? Are we alone? How will the universe end? These questions drive cosmology forward, each answer revealing deeper questions beneath. But for now, as you lie here listening, allow the cosmic perspective to bring peace. You are ancient stardust, assembled into intricate patterns that can think and feel and wonder. You are connected to everything that ever was or will be. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all were created in stars billions of years ago. The universe is both impossibly large and intimately small. The same laws that govern the largest galaxy clusters govern the atoms in your body. The expansion of space carries distant galaxies away, but the forces within atoms hold you together. You are balanced between these scales, a meeting point of the cosmic and the quantum. As your thoughts slow and soften, imagine yourself floating in the cosmic dark. Around you, galaxies drift like snowflakes in an infinite void. Beneath you, the fabric of space-time curves and flows. Above you, if there is an above, the cosmic horizon marks the edge of what can ever be known. You are here, now, part of this vast and ancient story. The universe began in fire and will end in ice, or perhaps in fire again, or in a rip, or in ways we cannot yet imagine. But in this moment, in the middle chapters of cosmic history, there is structure and complexity. There are stars and planets. There is life. There is consciousness. There is you. Let the weight of cosmic time cradle you. 13.8 billion years have led to this moment. Countless events, from the inflation of space to the collision of galaxies, from the formation of the sun to the evolution of life, have conspired to create the present. You are the universe's gift to itself, awareness emerging from matter. Rest now in the knowledge that you are part of something vast and beautiful. The cosmos that created you surrounds you still, holding you gently in its laws and its rhythms. The same darkness between stars embraces you as you drift toward sleep. The same timeless patience of the expanding universe allows your thoughts to slow and cease. Close your eyes and feel yourself expand. You are not separate from the cosmos, but woven into it. Your atoms will one day return to space, perhaps to become part of new stars, new planets, new forms of existence we cannot imagine. For now, you are here, conscious and aware, a brief pattern of order in the universe's long dance between chaos and structure. Let go of questions and calculations. Let go of distance and time. Let go of everything except the simple fact of existence. You are, the universe is, and for this moment, that is enough. Drift now like a galaxy in the cosmic flow, slow and peaceful, ancient and eternal, part of everything that was, is, and will be. Good night, cosmic traveler. Rest well in the cradle of space-time.